So if I want to do an oil can that holds a liter, 1,000 cubic centimeters, and I want to find the dimensions to minimize the package cost. Basically, I want to minimize the surface area. You guys agree? And this, a good old-fashioned oil can like this from the good old days. Nope, you got to do both. And you know, in the good old days, we take our little pie opener and put 2 holes in and pour it in. You don't need to have those, but that's what oil cans look like. And if I'm going to do this, I'm going to minimize the surface area. And I said the volume holds 1,000 cubic centimeters. So the first thing is I have 2 equations going on. Like almost always this happens. You guys read the volume of this situation is 1/3 pi r squared h.
For the green to the middle school bathroom, for the green to the middle school bathroom.
All right. And the area, you guys agree the area, if I drew a net of it, it's like this, right? So the area of this can, I'm going to call it A, is 2 pi r squared plus, all right? You know the circumference of the circle here because students invariably apply it incorrectly. All right, so I got this, right? We know the area of a circle is pi r squared, and we know the circumference is 2 pi r by h. So there's the area, and there's 2 of the circles. All right, so there's our surface area. And I want to minimize A, right? Everybody, I want to make this as small as possible. I want to keep our packaging cost tiny. All right, here's the problem. R, and H. And remember what we talked about. If we're going to optimize, minimize, maximize, this is not about time. You have to have 1 variable. And this, my friends, has 2. All right? Now, it is not coincidental that I gave you the volume up here of a liter, which is 1,000 cubic centimeters. Oh, you're back. I'm not sure I'm picking up exactly in the video where I left off, but we'll just go from here. So we have an equation that we know we want to optimize. We want to minimize A. All right? But it has 2 variables. So one of them has to go away. I was given a volume, so I'm going to plug that number in place of V. And what you should see here then is that I can solve that volume equation either for R or H. And guys, when I see this thing, it doesn't matter too much. I don't like square roots that much, so I'm going to solve the black equation I just wrote for H. Yep, it is actually. So I'm going to solve this for H by multiplying by 3, dividing by pi r squared. And H would equal 3,000 over pi r squared. And this is good news, because now I can use this piece of information in my area equation to develop an equation that is in terms of 1 variable. When we optimize, we have to get to 1 variable. All right? So if I get the new equation, I'm going to write A equals 2 pi r squared plus 2 pi r, and H is 3,000 pi r squared over pi r squared. And I can do some simplification. I'm going to change the view down to about 75% so we can see it. And now I can do this. I can go, okay, hey, A equals 2 pi r squared. We see on the second term, I'll do it in red, that pi's cancel, right? And instead of, I have r over r squared, so I can write this as 3,000 over r. Or I can write this whole thing as 6,000 r to the negative 1. Because I know if I want to minimize or maximize, find local mins or maxes, I need the derivative. So I have this derivative now in terms of r. So now I can find A prime. A prime. All right, and every time.
So that's not the derivative.
No, this is still the function.
Okay.
Now I can do the derivative of this function because it's in 1 variable now. Take the derivative of 2 pi r squared. How about 4 pi r? the derivative of positive 6,000 r to the negative 1. Negative 6 r negative 2, right on. We know that critical points are where local max and mins occur. So we want to know when a prime equals 0. All right? If I do that, I get 0 equals 4 pi r minus 6,000. I'm going to put it over r squared. You guys agree the radius can't be 0, right? It can't be 0 in real life. Because if we're going to find a max or min, we're going to look for the critical points. So we set the derivative equal to 0. That's how we optimize. Good question. So now I'm going to multiply everything by r squared. And this is the type of answers you guys hate, because this is going to be the answer. Move 6,000 to the other side, divide by 4 pi, and I still have to do what? Take the cube root. So r is equivalent to the cube root of 6,000 divided by 4 pi, if I leave an exact answer. I don't particularly want an exact answer in this case. Yeah, I suppose I can simplify it that way.
1,500.
Yep.
Yeah.
Yep, so we can do 1,500. And then you can search out probably some numbers here. So we can do this. All right. And if I cheat,
Under 500. Or no, that would be scary.
so,
11.
yep. So at this point, I've found now the radius. And if I want to prove that this is a minimum, guys, it's pretty easy. If I come back up here to the first derivative, I take the second derivative in green. You guys agree the second derivative is this? 12,000 r to the negative 3. Now think about it. I don't care what r value is. Any r value I plug in here is going to be positive. 12,000 times a positive plus a positive is going to be positive. The second derivative rule states that if the first derivative is 0, the second derivative is positive, we have a local min. This is a minimum value. So if I want to find, so now I know this is a minimum. I just proved it. If it said justify, that's the way I personally would justify it, by using the second derivative rule.
Like what made it? I didn't hear.
I said, how do we know? How do we know for sure that this is a minimum value, not a maximum? How do we know that r equals this is a minimum, not a max? We know it because we can check the first derivative rule or the second derivative rule. Yeah, I just did the second derivative rule in green. Yep, I did the second derivative in green, just to show you. But guys, right now we don't need to do that. I'm just rolling back. All right, it said find the dimensions. Everybody, the dimensions here. I have the r. If I want the h now, there's h, right? I just have to plug r into it and simplify. And we have found the radius. It's terrible, but again, I much prefer to do a decimal here, guys. I'm going to do a decimal. I'm going to change this r at the bottom. Oh, yeah. Because, no offense, how do you tell somebody to build a can 1,500 divided by pi? You know what I mean? That's just something that we...
Good luck.
Yeah, good luck. Go build this can. You know, that just doesn't happen. I mean, I talk a lot about this and joke around, but we don't. Carrot hat, 0.3. I get 7.82 centimeters. All right, that's the radius of the can. If I want to find the height now, I can plug that back into the other equation. H equals 3,000 divided by pi times 7.82 squared. All right? Yeah, no fun is right. I get 15.62. For round numbers, again, I rounded. 62 centimeters. Now the irony here, guys, is that you're going to see the can is almost the same diameter exactly as it is tall. All right, and that's actually something we can prove. All right, and is it getting too small for myself?
Well,
The board, or you got?
well, there.
You're seeing the board. Oh, you got the board. All right. So guys, we just figured out the can. If I come back, I go to a new page. 7.82 by 15.62. This can is pretty symmetrical.
Why is
Well, probably by rounding error, because if you think about it, rounding, then I squared.
So it is supposed to be.
You can probably.
exact.
So 7.82. If that's that, we're going to do that twice. If I draw this to scale, it looks just
Oh,
like
no.
this.
Um,
Guys, and that is the optimum can. Guys, they didn't sell liters in the United States of oil, okay, back in the day. They sold quarts. And if you sit down and figure it out, the can that the old guys used, the tin cans for oil, were very close to optimal. I will say this before I end the video. Nowadays, packaging is so important, they rarely care about what optimizes the material for the stuff inside. I mean, look at a cereal box, guys. Why is a cereal box so tall? It's 12 inches tall, and it has 8 inches of cereal in it every time, right? It is optimized to the shelves in the store. Because, I don't know if you know this, but you pay money as a manufacturer to where you sit on a grocery store shelf. You pay money to be in the middle of the shelf. You pay, that's why generics are on the bottom. They don't pay. All right, if you are an eye level, that is a premium spot. So when I worked at Hormel Foods, we used to design our packaging to be in that spot. But that was still an optimization problem, but not about content. It was about the shelf space.